guys.
Speaking of second order measurement systems.
Right. So, you know how we did first order measurement systems last time? We were like, this would be so much better if we had just one more order.
Double the fun.
Yeah, that's what we're getting today. And then on Friday, we will hopefully be finishing second order systems because it's going to take us 2 lectures to get there, at least. But we're gonna focus on like the foundation of second order measurement systems, and then we'll talk about free response, which might be a term that people are familiar with. Anybody familiar with the term free response from the differential equations class? Okay. So free response is the response to initial conditions. So that's the no forcing function. There are different terms that are used. I thought that one was common, so I used it. Okay, so let's go through. And I did fill in a lot of this stuff for you because I felt like there was a lot of material, and it's really easy to write something down incorrectly. And I'm a little worried about typos, but I did go through to try to double check, so we'll see. Okay, so second order measurement systems have input-output differential equations of this form, okay, where omega n is called the natural frequency, and zeta is called the dimensionless damping ratio. We don't say dimensionless, but it is dimensionless damping ratio. And f is a forcing function that depends on the input u, as shown in equation 312. So you can have up to second derivatives of the input, although we often will just have this last term with the u, and we don't have any derivative terms of the input. So it just depends, but that is more common. So measurement systems with 2 energy storage elements, such as those with an inertial element and a spring-like element, if you're thinking about a mechanical system, can be modeled with second order systems. So that's going to be quite a few of our systems are going to be second order. First and second order systems are very ubiquitous. For distinct roots of the characteristic equation, which is to say that they're not equal to each other, the homogeneous solution is, for some real constants, kappa 1 and kappa 2, this expression, where lambda 1 and lambda 2 can be written in terms of the damping ratio and the natural frequency there. We're going to see, I haven't given a physical interpretation yet of the natural frequency or the damping ratio, but to kind of give you a something to think toward as far as what those definitions mean. The natural frequency is, roughly speaking, the frequency at which a system will oscillate if you give it some initial condition and then let it oscillate. So for instance, if it was a spring mass damper system, for instance, the struts on a car, something like that, if you let it go, it will have some oscillation to it, especially if it's not very well damped. It will oscillate. Probably a bad sign if your struts do that on your car, but in any case, that sort of system is one that can oscillate, and the oscillation frequency is the natural frequency. It's close to the natural frequency. The damping ratio is, roughly speaking, how quickly that oscillation damps out. Okay, so the damping ratio we'll find is really a key aspect, a key parameter. That's why we write our differential equation in this standard form. We didn't just use, we could have used our A1, A0 notation here like we did before. But for second order systems, these constants have a really important physical interpretation, and that's why we define them this way. So what we see is that the roots of the characteristic equation have a real part, so that's the real part, right? And then they have this term, which could be imaginary, right? So if zeta is between 0 and 1, for instance, or actually between -1 and 1, notice that this square root is of a negative number then. What happens when we have a square root of a negative number? It's imaginary, right? We get imaginary. So we have a complex conjugate pair of poles if zeta is between -1 and 1. So good times ahead. Now, did anybody's differential equation class, because I know you guys all did second order differential equations, but did anybody use this zeta omega n notation, or did you guys use other parameters? Okay. So,
I never did.
okay. Yeah. I don't know. Just depends on where you take things, what people like to use, but there are others. For instance, somebody might have seen the Q factor, the quality factor, which is essentially the inverse of the damping ratio within a factor of 2. So, okay. These are, I would say, in mechanical engineering, these are by far the most common way of presenting it. In electrical engineering, sometimes you see Q instead of zeta, but otherwise, very common. So, we're going to focus today on the free response of this system. So, this is the homogeneous solution. Clearly, there's going to be particular solutions associated with the input, right? Whatever the input is, the forcing function is for this function. But today we're going to focus on just what happens with these systems if you displace them from equilibrium, from 0, and let them go. What happens with the system? And that'll be our first sort of interrogation into how these second order systems behave. And I think it gives us a foundation for our intuition, and it's easier than any of the forced responses. So we'll do free response first. So the free response, YFR, of a system is its response to initial conditions and no forcing. So the forcing function is equal to 0. It has, this is useful for 2 reasons. The first is that perturbations of the measurement system from equilibrium result in free response, making it critical. So if you have any, if you're measuring something, even if it's steady and it's not, there's no changing input, it's just like there's some constant or there's no input whatsoever, your measurement system is going to get a little bit of excitation from the environment. They always do. And so when you have that happen, how does the system respond? That's a critical aspect. And then another critical aspect is the second, that the free response can be added to a forced response. So there is a principle that we'll talk about extensively in system dynamics and probably in mechatronics as well, that states that for linear systems, you can find the response of the system to initial conditions on one side, and then you can also find the response of that same system to some forcing function, some input, with 0 initial conditions. And you can sum those two, and that result is the response you would get if you had the initial condition and the forcing function together at the same time. So you can treat them as separate problems, and then you can add them together at the end, which makes it really nice because then we don't have to redo a bunch of stuff. We can just treat them separately, hack off a chunk of problem that's manageable, solve it, and then add it to another one. So really useful. And so the free response isn't just useful when the forcing is 0. It's also useful when there is forcing. It's just that we'll have to add it to the forcing response. So more fun to come. So the free response is found by applying initial conditions to the homogeneous solution. So we're going to apply in this lecture, just to give us a little intuition, we're going to apply the initial condition y of 0 is equal to 0. Now, is equal to y of 0, or y 0. And then the y dot at time equals 0 is equal to 0. So this is one possibility. The other possibility is that you have, well, there are two others, right? Y dot is also non-zero. That's possible. Also, you could have both of them being non-zero. So those are the possible combinations. But note that the special case that we're taking right now, this is probably the most common one, is that there is some initial disturbance from equilibrium, and not that there's some initial, say, velocity or derivative of this disturbance. So this is sort of the paradigmatic case of an initial condition. All right. So if you have these initial conditions, the free response is found by essentially just applying that initial condition to the homogeneous solution right here and solving for what your kappas are. So we could all do that, but it's done for you here. And it's pretty much the initial value multiplied by some constants multiplying e to the lambda 1t summed with e to the lambda 2t. So not really surprising, given this was the form of the homogeneous solution. This is the form of the homogeneous solution when we apply these initial conditions. So that's cool. So there are 5 possibilities for what this implies. Notice that this is the solution for distinct roots. If you have repeated roots, if lambda 1 equals lambda 2, you have to put a t in here. And we'll talk about that. It's one of the 5 cases. So, okay. So these roots have sort of 5 distinct possibilities. Okay. So they are, first off, that zeta is between negative infinity and 0. So if we look back here, if zeta is negative, okay, omega n is always positive. So if zeta is negative, omega n is positive, that means that this real part here is going to be positive, right? If the real part is positive, then notice that the real part's the same for each of these lambdas, right? So you're going to have kappa 1 e to the, I'll just put a plus sign for positive times something else, right? Whatever goes on over here. And you're going to have plus kappa 2 e to the plus times something. You can factor out this e to the real part that's positive here. And it's going to be e to the something positive times whatever else your response is. And what does e to something positive look like? Yeah, it's an exponential. And even if it could be times a cosine or something, it could be sinusoidal, but also exponentially increasing in amplitude. So that's bad news, right? That's not what we like to see. So that means that we'll talk about what this means more in other courses, but it means that our measurement system is unstable, and given any non-zero input or output, it will explode to infinity. Boom. It's not a good look for a measurement system. Okay, so there's one of our 5 cases. Probably just like we're just going to assume we're never going to have measurement systems that are unstable, and if they're unstable, we need to redesign them. Yeah.
So this principle is the same for any kind of, if it's a measurement system or physical system that
Right.
it's not damped properly, it will oscillate to the point where it just explodes.
Yeah, and now for mechanical systems that are well, so the easiest unstable mechanical system that I can think of is the inverted pendulum. So you could try to model the inverted pendulum, but if you perturb it at all from its equilibrium, it doesn't want to go back to equilibrium. It wants to go away from equilibrium. It's never going to come back. So that is an unstable mechanical system. And yeah, it's something that we can improve using feedback control. And actually, I have a piece of equipment that I just got like Monday that is an inverted pendulum, and you can control it. You can balance the pendulum, sort of like you balance a broom on your hand, like it does that. It's pretty sweet. Okay, so unstable systems, they're bad measurement systems because if you have any value that is introduced to it, it's going to go off to infinity, and it's not going to indicate, the output's not going to be reflective of any input. We're supposed to be having the output reflect the input, right? That's what the measurement system's supposed to do. If the output's not reflecting the input, it's not good. And if it goes off to infinity and the input's just sitting there, not going off to infinity, then it's not a good measurement system. So those don't really, I mean, that would be very uncommon to have an unstable measurement system. So we'll just say, if we find that our measurement system is unstable, we will go back to the drawing board on our measurement system, make it stable. Same with an undamped measurement system. So an undamped system will oscillate forever if perturbed from zero output. So for instance, if you come back over here and you look, if zeta equals 0, there's no real part, right? And then zeta is equal to 0, so this is just the square root of -1, making this just the imaginary number, times omega n. So if you give this thing any initial condition, it's just going to oscillate forever, which once again isn't going to reflect what's going on in the system. It's just going to be oscillating. So I mean, you could think of, and actually a regular pendulum is a good example of a system that's going to oscillate forever. It slowly damps out, but it doesn't damp out very quickly, right? I mean, you can have some pendulum that you can create that are very, very low damping. There's one in the physics building at, I think it's at UW, yeah. And it's like,
does it tell time?
I don't think it tells time.
It just moves if you're in. So if you go to have like an hour or 2 hour long class, you like go back out and it's changed direction.
There's one at my old school that they set up dominoes around it every day, and it proves the motion of the earth, but it just keeps swinging, and it changes, and it knocks dominoes down as it goes throughout the day.
That's cool.
And then they reset it every day.
Yeah. But yeah, it doesn't lose energy very quickly. It does lose a little bit of energy every swing. Has to move all the air. There's a little bit of heating that happens inside the cable, but yeah, it's very minimal. So yeah, there's some systems that are approximately, I guess, undamped systems, and you can create some using feedback that are undamped systems. Oscillators, but that's once again not a good measurement device. Good for some things, not good for measurement. So we're going to also assume if you have an undamped measurement system, unless you're doing something very specific with it, you're probably not going to be using that for your measurement system. So we're going to focus on the other three cases, okay? The underdamped is the first one, which is for zeta between 0 and 1. So roughly speaking, underdamped systems oscillate, but not forever, okay? Let's consider the form of the solution for initial conditions and no forcing. The roots of the characteristic equation are negative zeta omega n plus. Now, notice the only thing that's different from the general roots is that the 1 minus zeta squared used to be zeta squared minus 1. But we have determined that zeta is between 0 and 1 just by saying it is that way. We're assuming it's that way. And if it's between 0 and 1, then you're going to end up with a, when it's zeta squared minus 1, you're going to end up with a negative number in the square root. So what we're doing is we're just factoring that negative number out, and we're placing it out here, j, and we're saying it's 1 minus zeta squared. So that is our solution to the characteristic equation. So negative zeta omega n plus or minus, and we call this term the damped natural frequency, omega d. And as we'll see, that's the actual frequency at which the system responds when it's in free response. So if you want to be a little bit more precise, it's not the natural frequency, it's the damped natural frequency. If it's totally an undamped system, it does respond at the natural frequency, but any underdamped system will respond at the damped natural frequency. So notice how close it is to omega n. It depends on how close zeta is to 0, right? So from equation 315, for the free response using Euler's formulas, to write in terms of trigonometric functions, so remember that complex exponentials, like we have here when lambda 1 and lambda 2 are complex, we can use Euler's formulas to rewrite it in terms of trig functions. And with these initial conditions, so with some output offset and no derivative term, we end up with this relatively simple expression, which let's unpack for just a moment. So here's the initial value. We have this oscillation, this cosine omega dt. So it's a cosine that's oscillating at the damped natural frequency, and it has a decaying term out here, e to the negative zeta omega n. So this is something that's oscillating but decaying, right? So we could think of, so cosine's maximum value is 1, right? So we could think of this as being cosine going along, and then e to the minus zeta omega n t is an envelope to it. So if you've got like, yeah, so like this is the e to the minus zeta omega n t, and here's so the cosine would be, you know, like this. And so it's getting multiplied. And so it's getting the sort of envelope. And then the phase is just this expression. This is an oscillation that decays to the value it oscillates about as it approaches infinity, which is 0. So any perturbation of a critically damped, and that is a typo. Any perturbation of an underdamped measurement system will result in a decaying oscillation about equilibrium, which is 0. All right. So progress, we've got one type that actually works, right? It's actually valid. It's a start. Zeta equals 1 is the critically damped case. So in this case, the roots of the characteristic equation are equal to each other, and they're real. So we must modify equation 3.13 the factor of t for the homogeneous solution. Do you guys remember that from differential equations, second order system? Repeated roots, you had to multiply by a factor of t.
For each term that is repeated.
Right. So yeah, so if you had, for instance, 3 roots that were repeated and then one that was different, then you would have to have a factor of t on one of the repeated root terms, e to the lambda t, and then you'd have to have a t squared on another one, and then the other one wouldn't need a t. It would be fine. So the multiplicity factor.
That's the way that the reason we did this is how we would have we wouldn't have like I don't remember there was a reason for it that it was kind of arbitrary to add it in because we didn't want to repeat ourselves. So.
Yeah, it's because you're only left with one solution, and you need to have multiple distinct solutions. Because in this case, if lambda 1 equals lambda 2, then you have e to the lambda 1 t, but that's equal to e to the lambda 2 t. So they're not two. It's not two expressions. Not two solutions. So we must modify it for the homogeneous solution. The free response for initial condition, once again, an initial value for y, but not for y dot. I'm using dot for derivative here because I think it's a little more compact. And we aren't exclusively working with electronics, so I'm not afraid to use dot. But I'll switch back and forth. So we have y free response equal to the initial value times, we see this factor of t show up. But notice, so t is increasing, e to the minus omega nt is decreasing. Who wins that battle? The linear function or the exponential? Exponential wins, right? So even though t is always increasing, exponentials is decreasing faster. So, yeah. So this decays without oscillation, but just barely. So it doesn't oscillate, but we're going to see that like it's on the verge of oscillation. Like it could, if it was a little bit less damped, it would oscillate. Okay. Now, overdamped. Zeta between 1 and infinity. Here the roots of the characteristic equation are distinct and real. From equation 315, with free response to initial conditions, we have the sum of 2 decaying real exponentials. Okay, so that's not very exciting. And actually the expression is kind of gross in terms of zeta and omega n, so I didn't include it. It's pretty long. But you can always just go back to the general solution, which we said is 315. So this is any free response as long as there's no repeated roots. So if lambda 1 and lambda 2 are both real, you just plug into this expression. It's not too bad. If you want to express that in terms of zeta and omega n, however, it's pretty bad. So I don't recommend using that form. If you want to see that form, though, it is in the System Dynamics book, the Rao and Wormley book. It's in there. It's not pretty. Okay, great. So those are all possibilities for our system. And if it has 2 decaying exponentials, obviously it's not going to overshoot, right? They're decaying real exponentials. It's not going to overshoot. So it's just like the critically damped case, and I actually thought this was fun, but with even lesser gusto. So there's that. So figure 3.7 displays the free response results, and
Much better in color.
yeah, I bet it is better in color.
It's super interesting here.
It's grayscale.
It's the
this shade of black is slightly less than that one.
Yeah, it would be hard to pick up what side because I go from blue to black to red,
So
and
which,
so
the
the
point
blue,
one, point one is the one that looks like a
the one that oscillates.
yeah.
So notice, so this is 0.1. That's what do we call that? Underdamped. So that's underdamped. What about 0.3? 0.5. Underdamped. So these are all underdamped. Under a little more room, damped. So these correspond to the blue ones, and notice that. So what let's look at the scales for a minute because they're a little bit confusing at first. I really need to convert you guys into believing in things like dimensionless time. It's amazing. Dimensionless time is great.
What? This is 4 times. That's it.
So dimensionless time is used a lot in graphs like this because these graphs you would have to have one of these at each zeta for each omega n, right? But it turns out that in the expressions, all of these expressions, time is always multiplied by omega n. So if you make that your new variable, omega nt, which happens to be dimensionless because radians per second times seconds, and so the seconds cancel. So rad time. Thank you. Yeah. So it's
This was instrumentation.
it. I think it's maybe like the School of Comedy. Yeah. So that's the horizontal axis. So if you wanted to know for a given omega n how to read this, so you say, okay, what would it look like for zeta equals 0.1 and for some given omega n? What would you do? So it's just a scaling in the horizontal axis. So if omega n is equal to 1, then it would look exactly like this. If omega n was equal to 2, then you would have to divide this. You'd essentially it would squish this in. If omega n was equal to 0.5, it would stretch it out. So it allows you to put a lot of plots on one graph without having to choose a specific value for a parameter. So it's really useful when you can use it.
Omega n is like a scalar.
So omega n, yeah, so it's just a natural frequency, whatever it happens to be for a system. So in this case, I didn't have to choose it because I used it as a variable. I used omega nt as my x variable. I could do it because every time t showed up in my equation, omega n was multiplied by it. You can't do it if that doesn't occur. But in this case, it does occur, so you can get away with it. And we always look for those. We look for those situations. So try to look for them when you're working on things because it allows you to simplify graphics like this. You don't have to do it for a bunch of different cases. It's valid for any. So there's a really long tradition in engineering of making really, really information-rich plots and charts and graphs. And some of the most ingenious things I've ever seen are engineering diagrams that people have spent so much time packing information into. And it's not exactly a lost art because people still do it in figures like this. But it used to be that was, like those charts were not just used for getting intuition. They were like, those charts were used to find values on that you used in calculations. So less frequently do we need to do that now, but we use them for intuition. So I like to make mine a little less information rich than some of those, which can take hours to even get like a feel for. These ones hopefully don't take that long. So this is the, and then the vertical axis is the normalized output. So also notice that everywhere in all of these solutions, y naught shows up as a factor. So you can divide both sides by y naught, and you get an expression over here that doesn't depend on y naught at all. So this is valid for any initial output y naught. And if you wanted to, if your actual y naught was like 5, you would need to multiply this value by 5, right? And it would stretch vertically. So these sorts of plots are really useful. Okay, so notice that for underdamped systems, it overshoots and it oscillates. For a critically damped system, the black one, it doesn't overshoot and it doesn't oscillate, but just barely. And then for overdamped systems, it doesn't oscillate and it doesn't overshoot, but it slowly oozes its way back to equilibrium when it gets perturbed. It's the slow ooze. Yeah. Cool. So note that that a small damping ratio results in overshooting and oscillation about the equilibrium. In contrast, large damping neither overshoot nor oscillate. Good. For this reason, the damping ratio of a measurement system should be close to 1. Okay. There are trade-offs on either side of zeta equals 1. Slightly less than 1 yields faster responses that overshoot a small amount. So for instance, if you see this zeta equals 0.5, it overshoots and it oscillates just a little, but notice how much faster it gets to this initial value compared to, for instance, this guy here on the other side, which it doesn't overshoot and it doesn't oscillate, but it takes a lot longer to get there. So it's a trade-off. Depending on your application, you might want to be a little bit underdamped or a little bit overdamped, or maybe critically damped. Somewhere in that region, though. You're going to want to be not too much oscillation. You don't want to have too slow of a response. You want to, some sort of medium that works for you. Okay, good. So that brings us to our example. Oh no.
Yay, the answer. It's filled in.
It's filled in. Let me open up a new copy.
It is
Just a sec. I need the partial. And second order measurement systems. Okay. It's just 2 pages of the example, right? Yeah. Just 4 and 5. All right. So, as proud as I am of the solution I wrote up, it's more useful for you guys for me to do it live. So, in magnetic resonance force microscopy, MRFM, the primary detector is a small cantilever beam with a magnetic tip. Model the beam as a spring mass damper system with mass equal to 6 picograms, spring constant equal to 15 millinewtons per meter, and damping coefficient equal to 37.7 times 10 to the negative 15 Newton seconds per meter. These might all seem like really small values to you. They are. I took these actually from a paper that was written. So this is the technology I work on. So this is real life, people. So what is the natural frequency? What is the damping ratio? And in free response, how long before the amplitude must be less than 10% of its initial value? So, a lot of stuff there. I actually kind of feel like I don't want to rush us to this example, so I'm gonna push it to Friday. I have mixed feelings. I might.
You're ending before 50?
I mean, so
It's 3:49.
I guess here's my thing on it. I could just continue on, and if you can stay, then that's great. How many people can stay and would be willing to, or how many? So let me ask that. How many people can stay or would be willing to? I mean, I realize that you don't all like have to be here, and you might have something to go to. Okay, so like most of you can't stay. It's probably gonna take 15 minutes.
Okay.
Yeah. What about? It sounds like, but most of you can't stay for 15 minutes. Yeah. So I won't keep you. This is when, if I had my video lectures uploaded more promptly, I would say, just watch the video for the rest of it. When I get my videos going, I'll often put in little extra lectures in between lectures, because I'm like, oh, I'll just do another example problem, and I'll just like do it and then upload it. So hopefully soon I'll get that.
I had a physics professor that did that for our classes.